In Lesson 3, we are going to learn how to work with the actual code in the LTE application framework. In other words, we are going to learn how you can use the LTE application framework for your prototyping. We're going to go through some basic considerations, we're going to go through how to reuse existing modules, and then we're going to discuss writing new modules. The FPGA code of the LTE application framework is architecturally broken down as seen on this slide. At a high level, there's one overall system running on the FPGA. This system is made of multiple different clock-driven loops. Within each of these clock-driven loops are code modules, and within each of these code modules are submodules. When starting to modify the application framework from the lens of this architecture, you must ask yourself a few questions. At a high level, you want to ask, how does my planned system differ from the existing system? Are you adding new functionality? And if so, can you reuse the existing modules or submodules, or do you need to rewrite them from scratch? If you are rewriting them from scratch, what design language should you implement your new functionality in? Other questions include whether you need all of the existing functionality, which parts can you keep, and which parts could be removed. The answers to these questions manifest themselves in two primary approaches for building your system. The first is what we call top-down, in which you start with the existing system and edit specific modules or add new modules. In this case, you're reusing most of the existing application framework, but you're making some changes or implementing some new blocks. The other approach is what we call bottom-up, in which you build your own system by reusing existing modules and submodules. So say you're working to create a new communication system, but you want to reuse specific components of the LTE application framework, such as the encoding or decoding or the modulation schemes. In the rest of this lesson, we're going to look into how you can reuse existing modules or how you can add new functionality to the application framework. Let's start with looking into how you can reuse the existing modules in the application framework. First, let's recap the available modules as covered in Lesson 2. In Lesson 2, we discussed the transmitter and receiver implementations in the LTE application framework. Briefly, the transmitter implements a resource mapping, channel encoding in the data and control channels, and OFDM modulation, which includes an inverse Fourier transform and cyclic prefix insertion. The receiver implements synchronization, including CFO compensation, OFDM demodulation, channel estimation and equalization, channel decoding for both the data and control channels, resource demapping, and also real-time configuration of the data channel based on the control channel. The first thing to be aware of when looking to modify existing blocks in the application framework is all the documentation available for those blocks. The first thing that you can use is what is called context help. When you are looking at the actual code, if you hit Control and then H in LabVIEW, and then hover over one of the blocks, you will see documentation available for most of the modules. This documentation will include functionality of the module inputs, the module outputs, and timing information such as the actual latency of the module. In addition to this, the LTE Application Framework white paper online describes the framework in a full system context. In this white paper, you can look at the high-level architectures and blocks and how they were implemented as compared to the standard. When modifying or reusing code in the existing LTE application framework, we have some key recommendations. The first is to remember that the functionality of the existing module can be reused as is, and what you are really doing is taking that existing functionality and either modifying it or adding extensions. If a test bench does not already exist in the project, we highly recommend building a test bench to better understand the behavior of the existing module in simulation. This allows you to run the module, see how changes affect it, and then give you a template to start to modify it all in a simulated environment so that you do not have to wait for lengthy FPGA compiles. We also highly recommend leveraging a new feature in LabVIEW Communications 2.0, which are sampling probes in your simulation, which gives you the value of different wires on a basis of the actual clock cycle as it progresses over time. In exercise 3.1, we're going to walk through building a test bench for FPGA code so you can understand its behavior and then have a starting point from which to then modify that code. All the LTE application framework modules are written in what is called clock-driven logic in LAVI communications and stored in gcdl files. CDL logic, in addition to all other FPGA models of computation, can be simulated on the host. And with the CDL file, you specifically will use the Run FPGA Simulation node. Let's build one and see how this works. All right, to create a simple test bench, let's start in the System Designer. You can get to System Designer by going to View and then System Designer in LAVI Communications. The first thing you want to do, if you do not already have one, is to prepare an FPGA target. In this case, it's just going to be a simulated FPGA target, and you can just choose one of the USRP RIOs from the left palettes. Then you're going to create a new GVI file and drop it onto the host. This is going to serve as the host test bench that's going to stimulate our FPGA code and actually look at the outputs to see if they're what we expect. Then you are also going to create a new .gcdl file and drop it down onto the FPGA. This .gcdl file is going to be the actual FPGA algorithm that we're going to implement. Now go ahead and open up the CDL or clock-driven logic file that we just created on the FPGA. What we're going to do is create something simple so that we can explore how creating an FPGA block actually works and how we can simulate it. Identify a block that you would like to study. As an example, try the discrete delay block, which you can access by hitting Control Space and then starting to type discrete delay. You can create inputs and outputs for all the terminals of the discrete delay node by right-clicking on those terminals and saying create input or create output. As needed, you can use the int to fixed point conversion nodes when necessary to make sure that your data types are proper. When you select each controller indicator, in the right rail in the properties, make sure you select on the connector pane. And then right-click on the wires and place sampling probes on the wires. We will show you what this looks like in a few slides and also in a demo of this exercise in just a little bit. Now let's open the VI on the host, which we're going to actually use to create the test bench harness around our FPGA algorithm. First, in a host VI, drop a Run FPGA Simulation node. You can do this either by going to the Hardware Interfaces palette or by hitting Control and Space and then typing in Run FPGA Simulation. Go ahead and drop this on the diagram and then right-click and go to Properties. And then the right rail, configure it to be the proper FPGA target, which is going to be just our simulated USRP. And then also select the name of the block that we created in the previous step. Next, surround the Run FPGA Simulation node with a for loop. Then create input signals as needed, whether they're arrays or constants, and you can use the matchscript node to actually create the test vector to stimulate your algorithm, and then press the Run button. As mentioned, we'll show you what this actually looks like on the next slide and in a demo. For our example, our FPGA block, which is a variable delay block, looks like what we see at the top. And then our actual test bench, which is called Simulate Variable Delay, looks like what we see in the bottom. To describe what we see in the variable delay CDL block, we have our discrete delay block that we drop down. We have data that comes in, and then we also have the delay that we're going to use. And then finally our output, and also an enable signal. On the test bench, we create a test vector written in M using a matchscript node, and then we feed that into a for loop that's going to continually run our FPGA block for as long as we need to get the proper outputs and confirm that it works. To help understand what just happened in our simulation, it's best to observe the sampling probe window. The sampling probe window should have popped up when you right-clicked on a wire earlier and said Create Sampling Probe. What the sampling probe allows us to do is look at the value of certain wires over time with respect to the actual clock that the algorithm is running against. What we can find are a few things. First, we found that the sampling probe collected 50 different iterations. This is equivalent to the size of the initial array on our host testbench. We then see that when the enable is true, we see a delay of 5 cycles before which we see an output. However, when the enable is false, the discrete delay module just holds the subsequent value that it had. So this simulation allows us to have a view of how this block works with respect to the enable signal and the data that's going through it. All right, let's look at another example in exercise 3.2. For exercise 3.2, go ahead and open up exercise32.lv project, which came with the source files for this training. Then open up main.host.gvi and switch to the diagram so you see the source code pictured in the slide. As mentioned, this is the test bench that is going to run on your host to simulate and stimulate your FPGA block. Familiarize yourself with the source code. In the diagram, find the Run FPGA Simulation node. As in exercise 3.1, this node is going to encapsulate the actual FPGA block that we're going to create. Go ahead and study its inputs and outputs, and open the corresponding gcdl module by double-clicking on the node. Next, find the helper module index generator host. Study the structure and dimension of its outputs. Here are some questions to help you understand the exercise. We will look at the answers to these questions on the next few slides. First question is, what is the size of the array that is created in index generator host and why? The next question is, how many times is the for loop with the Run FPGA simulation node executed and why? Why do we need to filter for valid elements after the FPGA simulation? Assuming the latency of the module is known, could the function filter valid elements be replaced by something else? All right, let's look at the answers to these questions. To the first question, what is the size of the array that is created in index generator host and why? We need to think about how a radio frame is structured. The module itself iterates through one complete radio frame once. As we saw previously, we know that a radio frame includes 12 subcarriers per resource block, with 100 resource blocks per radio frame, with 14 OFDM symbols per subframe, with 10 subframes per radio frame. So if we do the math, that means that there are 168,000 elements in this array. Then, how many times is the for loop with the Run FPGA simulation node executed and why? And the answer to that question is 168,003 times. We added 1 dummy data before and 2 dummy data after the valid data to compensate for latencies in the gcdl code. Why do we need to filter for valid elements after the FPGA simulation? Well, the purpose of the valid flag is to indicate data that should not be processed. In this case, the dummy data that is added produces invalid results in the beginning and at the end, and we want to be able to be sure that we are aware of this so that we don't process this invalid data later down the chain. And then assuming the latency of the module is known, could the function filter valid elements be replaced by something else? And the answer is yes. We could ensure that the loop is executed and then manually select the valid subset of the output array. Okay, now the question is how to actually modify the FPGA module. Open up the source code of the FPGA module, which is going to be called LTE Physical Channel ID Mapping DL.gcdl. Look at the structure of the input terminal, timing indices, and the output terminal channel cluster. From the output, trace back the PDCCH signal. Modify the condition under which symbols are marked as PDCCH, such that PDCCH occupies the first 2 symbols of a subframe, and test your simulation. To help, this is what it looks like. Here we can see the channel cluster output, and we can see where the PDCCH data gets fed into this overall output cluster. From here, let's trace back to the original PDCCH signal. If you're lost, remember that we are in the .gcdl FPGA block, and this is what we're going to try to modify before we go back and run the host. Now let's modify the condition under which symbols are marked as PDCCH such that the PDCCH occupies the first two symbols of a subframe and test it. If we trace back into the code, we can look and see that we have a part in the code where we look and see whether the symbol index is equal to 0, and if so, that is the PDCCH. If we replace this block to look and see whether the symbol index is less than 2, in other words, if the symbol index is equal to 0 or to 1, then make that the PDCCH, then this will make us successful in our goal. It's as simple as that. Now go ahead and go back to your host test bench and run it to actually verify that the output that we show here and the expected output that you're looking for is actually what you get. This is part of the beauty of an FPGA simulation, is you can just change the logic in a code, run a quick simulation, and verify that it is functionally correct before ever having to go through a lengthy compile. Finally, let's talk briefly about how you could write your own new module. What this really boils down to is the choice into what design language you are actually going to use. So far, we have primarily looked at clock-driven logic. This is the lowest level design language in Lavi communications, and it enables high performance, low latency, low resource utilization algorithms through manual optimization. This is covered in further detail in the Lavi communications course, lesson 8. The other two models of computation are higher levels of abstraction. MRD, or the multirate diagram, is a high-level design language intended for designs centered around streaming operations, in which a lot of the FPGA plumbing, like clocking and handshaking, are automatically handled for you by the compiler. This is handled in Lavi Communications Lesson 6. And then finally, the optimized FPGAVI, which allows you to use regular G code and for loops and other structures like that to do array manipulation or state machines, while leveraging the compiler to automatically unroll loops and automatically place feedback nodes. This is covered in Lavi Communications Lesson 7. In conclusion, you should use the right tool for the job, and really, you should continue to use the exact same workflow that we used when modifying existing blocks. In other words, create a test bench and simulate until you know that what you were trying to create functionally works. Also realize that within Lavi Communications, there are many examples and guided tutorials that can help you become more familiar with any of these tools if you've not been through the in-person customer education course. If you go to the lobby by hitting the home button and go to the Learning tab, you can explore all of these. These will help you get started on how to use the various techniques we described above and other techniques that are more advanced that we did not cover.